Gallman, and today I'll be covering Lab 4 for Physics 2211 on the topic of oscillations. This lab aimed to study and investigate the motion of a spring mass system moving in an arc. The goal was to test if the model follows the energy principle, which it did, showing the system's energy remains constant and at zero. I used Tracker to observe and track the motion of the object at the end of the spring from the video, and used GlowScript to create a computational model predicting ideal motion. For physics principles, I use Newton's second law, which says that the system's momentum change relates directly to the net force applied. Our setup had forces from both the spring, the upward force, and gravity downward force, which combined to form the net force. The energy principle is also essential. It describes how a system's energy shifts based on work and thermal exchanges with its surroundings. Here, our isolated system, the mass spring and Earth, had no outside interaction, so its energy should remain unchanged, consisting of only kinetic, spring, and potential energy. And here are the formulas for the three different types of energy present, and also to update formulas. Both derivations from Newton's second law were used in the computational model to update both velocity and position. I used a short video to track the observed motion using the Tracker software. The object had a mass of 0.402 kilograms, a stretched spring length of 0.7 meters. The initial position was at negative 0.117 meters in the x direction and negative 0.634 meters in the y direction, and had a zero velocity. The period of the oscillation and the spring stiffness were provided in pre-lecture video number 52, with values of 1.51 seconds for the period and a spring stiffness of 6.83 newtons per meter. In the coding phase, I set up these initial values, including the object's mass, the spring length, and the spring length, my apologies, the object's mass, the object's position and velocity, and additionally some constants were updated, such as the gravitational force, as 9.8 meters per second squared near Earth's surface, the spring constant, and the relaxed spring length. For the spring length and system energy of the section of the model, the spring length is the difference between the ball's position and the spring position, with L hat being the quotient of L divided by the magnitude of L. The compressed length is defined as the magnitude of L minus the relaxed length, and the relevant energy formulas were applied to their corresponding energies, and whenever you sum kinetic, gravitational potential and spring potential, you get the total energy of the system. The while loop then iterated through each time step, calculating energy changes. Knowing the net force at each step allowed for velocity and position calculations to be made using the velocity and position update formulas, and this revealed the system's kinetic and potential energies. For results, the graph showed an oscillating function. Initially, the models matched but diverged over time. As you can see here, it's pretty similar, and then over time they spread out more and more. Yet initially the models match but diverge over time due to real-world factors like drag and external forces performing work on the system, as it is not an isolated system in the real world. Possible sources of error include the system not being isolated in the real world, causing work to be done on the system by the surroundings as previously identified. Also, there may have been inaccuracies while positioning the center of mass on the object and tracker, leading to inaccurate coordinate points for the motion of the object. To address one of the discussion questions, does the energy principle hold? Given the isolated model, energy change should be zero, and the graph supports this with constant energy at zero, confirming the energy principle. I also compared oscillation periods in the x and y directions by averaging three consecutive periods for each. Results showed deviations across different directions, therefore affecting the spring constant and overall graph, as the spring constant in the x direction is 5.858 newtons per meter, while the spring constant in the y direction is 6.872 newtons per meter. And thank you. That is my lab 4.